Hello everyone, my name is Neha and this is the 17th lecture on Introduction to Microcontrollers. In this lecture, we are going to see the answer to the question which we saw in the last lecture, and we will also be covering some of the exercises based on reading and writing to the input ports, and then we will learn about interfacing the LEDs to the microcontroller. So let's get started. In the last lecture, we discussed the programming for rotating LED with the input button, and you can see this is the code we discussed. And I asked you one question at the end of the lecture that try to run this code and see what happens. If you have run the code, you know that there would be a delay in rotating the sequence, and that was my question, like how you can remove that lag. So to remove that lag, what we need to do is to use a status resistor. So let me show you. This is the status resistor which we'll be using in order to remove the lag, and you can see these are the 8 bits of status resistor, and each of them has some meaning. We have covered this status resistor, I believe, in the beginning of in the initial lectures also, but I'll quickly go through this. You can see starting from the 0 bit, this C is basically your carry, or you can see borrow bar, and if this carry is your 1, then a carry out from the most significant bit of the result occurs, and if it is 0, then no carry out from the most significant bit of the result will occur. And then this DC is your digit carry, and you can see that if this bit 1, if it is 1, then a carry out from the 4th low order bit of the result will occur, and if it is 0, then no carry out from the 4th low order bit of the result will occur. Okay, and this DC, it's mostly used with these instructions: add WF, add LW, sub LW, sub WF. So these are the arithmetic instruction set which you use. These are 2 for addition, these are 2 for subtraction. And this Z is your 0 bit. If 0 bit is 1, the result of an arithmetic or logic operation is 0. And if it is 0, the result of an arithmetic or logic operation is non-zero. So this depends what instruction set you are using and what is your output is coming out of the based on your code for the instruction set you are using. Based on that, it will set the 0 bit. And this PD is your power down bit. It is 1 after power up, or by the clear WDT is your watchdog timer. So this instruction means clearing the watchdog timer instruction, and 0 is when it is 0, then by execution of the sleep instruction. And then we have a timeout bit, and when this timeout bit is 1, then after power up, clear when the power is up. After that, clear watchdog timer instruction or sleep instruction is executed. 0, when it is 0, watchdog timer timeout occurred. So we are, but in this lecture and in the projects which you'll be doing, you will be mostly dealing with these 3: 0 bit, digit carry, and the carry. All right. So I'll show you how you will be using this status register into the code. So let's see next. So to remove the lag, you see here, this adjust is the label under the program. You remember we had one of the label named adjust, and in that adjust, we changed what we had previously to this bit test f skip if clear. So it is checking the status of status bit, and what is that 0 bit? 0 indicates your bit, right? If you remember the this particular instruction set. This indicates your file register, and then this indicates your which bit you want to work on. So we are working on 0 bit, and let's see what's there in the 0 bit. 0 bit is our carry bit. Okay, so it is checking the carry bit, and what it is saying, bit test F, skip if it is clear. So skip this step if the carry bit is 0, then skip this step and go to return. And if it is not 0, then again then call initiate init, or you can say initialize it again. So what it is trying to do is it is checking the carry bit. You remember, like, what we are trying to do here is we were basically rotating the LED with each button press, and then when you use that rotating instruction, then there is a carry involved with your 8-bit register. Okay, so with the help of this instruction set, what's going here is it is checking your carry bit. Instead of, there was one cycle which came in which that carry has to move to the register. Instead of doing that, it is just checking what your carry bit is, whether it is 1 or 0, and based on that it is executing the instruction. So let's say if it is if your carry bit is 0, then what it's going to do, skip if clear. So if the carry bit is 0, then it's going to skip this step, and then it will go to the return, and for the whatever the program is, it will go there. If it is not 1, then it will go to this initialize to this call, and this call was about your initializing the LED, again putting up or turning on the LED. So let's see the full code. So this is our the starting code. You remember, bank cell ncell P, clear F ncell P, making the port as digital, and then port A, bank cell select, port A, clear F, port A, port B, and then trace A, making all the port A as your output. And then move literal number to the working register, and from working register to the trace B. So when it is moved to trace B, then RB4, which is your button, is set as your input. Okay, and then call init. So we have to see where is this label. So if we look here, then we see label init is here, and then what it is doing, it is putting this literal number into this LED underscore pattern to this register, and if you can check where this register is, you see here, this is the register at this particular address, and then you have another register flag bit which is at this address. So I've already explained this to you in the last lecture, so hopefully you don't have confusion. So that's how it initializes, so making this RA4 as high. And then this loop goes in which you are doing the bit test for port B, and this 4 is your 4th bit here, which means RB4. It is checking that whether it is set or not. If it is set, then skip the step if it is set. So skipping this step and going to this step and checking it again if it is clear or not. And then if it is clear, then skip the next step and then go to this loop again, and if it is not, then go to call LED on. So this instruction, this will turn on your LED, and then it will clear the flag bit. And then if you go to rotate if needed, then in this one the mainly what is happening here, the rotation takes place. Actually not here, this basically set your flag bit, and then it's called for rotate now. So under this rotate, mainly the rotation takes place. You can see here under rotate now we have this call adjust, and this call adjust is the same thing which I showed you in the previous slide. So in the last code which you saw in the previous lecture, I mean the same code which you saw without with lag. In that one, instead of this status register, we had LED pattern, our general purpose register, which we have mentioned over here, and because of that there was a lag which we were getting. So what I did, I removed that LED pattern register, and instead of that I'm using this status register. And in this status register I'm checking the carry bit. Okay, I'm checking the carry bit whether it is 0 or not, and based on that the instruction will be executed further. The comment which you see here is from the previous code. I forgot to change it here, so please, this is not relevant to this status register. This is from the previous code, and you can set up your own comment over here. For example, you have used the status register, and in that carry bit is being checked. And then if the carry bit is clear, then skip the next instruction. Otherwise, execute the next instruction. Okay, so now you understand with such a small change how we can remove the lag. And I would request you to change this status register into your code and try to run this whole program and see how the lag is removed. Now the next thing which we are going to see are the simple exercise on reading and writing the input output into the input output ports. So in this we have a data direction which needs to be set before the input output operation. So you already know that, and you also know that to configure an input output pin for input, what you do is you set the trace register to 1, and to configure an input output pin for output, you set the trace register to 0. Now this is the example, and it says write an instruction sequence to output the hexadecimal value which is 0x33 to port D. And if you transfer this hexadecimal value to port D, what you'll do, you will first bank select trace D, or you can select port D. So that will be the instruction which will go here. Okay, and then you will clear F, which means you are providing 0 cross 00 hexadecimal value to trace D, which means you're configuring the port D for output, and then moving the literal value to the working register. This is the literal value we want in the port D, so you will move this value into the working register, and from working register to the file register port D. So these are the 3 steps if you want to output this hexadecimal value to the port D. So these are steps you will be using. Now we have few more examples here. Write an instruction sequence to read the current value of port D into working register. So now here, if you notice, what is different than the previous example is that here we are reading the value, okay, which means we have to configure this port D for input. And for that, what we have to do, we have to make trace a register as 1, like all the bits as 1. So which means we can use set F trace D, which will configure port D for input, and then move F instruction. You can use port D. What it will do, it will if you put here comma, let me quickly do it here. And so if you do like here comma and then 0, then what's going to happen, it's going to put the data into the working register. So move F port D comma 0, it will put the value which is there in the port D into the working register. And then let's see another example. Configure the upper 4 pins of port D for input and lower 4 pins for output. Okay, so what is the upper 4 pins? Upper 4 pins are basically your most significant bits, and lower is your lower significant bits. So most significant bits are on your left hand side, and your lower significant bit is on the right hand side. Okay, so that means we want to move something like and it says upper 4, which means F0 we will have to move. So this is the instruction: move a literal number to working register, and literal number is F0. And then what does it says? 4 pins of port D and for input, and lower four pins for output. And then move working register value into the file register, which is your tris-D. And this tris-D is going to have this value F0, which means it's going to have 1 1 1 1 and then 0 0 0 0. Okay, so you're making 4 pins as input and 4 pins as output. Now next we have interfacing with LEDs. So in many embedded system, it requires simple input-output devices such as your switches, LEDs, potentiometer, keypads, or like 7-segment displays. When you interface the LED, the purpose could be anything. For example, you want to show the indication that the power is on, or for example, in the project which you will be doing, like your alarm system and temperature indicator, you can use LED to indicate any output, for example, whether the alarm is arm or disarm. So you can use to indicate that operation with the LED. And in case of temperature indicator, whether the temperature is high or low, based on that you can indicate that output through the LEDs. And you know that LED can illuminate when it is forward biased and has sufficient current flowing through it. So the current required to light an LED may range from a few to more than 10 milliamps, and the voltage drop across the LED when it is forward biased can range from 1.6 volts to more than 2.2 volts. And these are some of the typical circuit connections which have been shown here, how you can connect. So output pins, and so here is your 5 volts, and then you see that a resistor is connected of 300, ranging from 300 to 500 ohm, and it is required to limit the current flow. So that's how you connect. And then here the cathode is connected to the output pin. So this is a low voltage on output pin light LED, and here this is the high voltage on output pin lights LED. So you can see that the output pin is connected to the directly to the resistor and then to the LED. And this is another way of using of connecting high voltage on output pin lights with LED. So you can see that here we have a NOT gate connected to the limiting resistor and then to the LED. So you provide so this side of the NOT gate is connected to the output pin. So here you are going to get whatever the you are getting over here is going to be opposite here, which will be your very low voltage, because or you can say nil voltage, so because that's what we want at here at cathode, because so this is the direction of the current flow in a LED, which means it is forward biased, and then only the LED will be basically it will light. So these are the 3 different ways you can interface the LED to the microcontroller. And then now let's see interfacing with 7-segment displays. So this is basically the circuit you can use which drive a single 7-segment display. You can see we have used here a port D, which has 8-bit resistor starting from RD0 to RD6, and this is connected to this this buffer chip, and this buffer chip basically drives the port D. So port D basically drives a common cathode 7-segment display through this buffer chip, which is 74HC244. All right, so this is used to display a few decimal digits. A buffer chip is often used to provide enough current to drive the displays. A one display circuit is shown in figure below. So this is one display circuit, which means you're using just one 7-segment display, and multiple digit display can be achieved by using time multiplexing technique. And to display a decimal digit, appropriate pattern must be output to port D. Now here the output high voltage value of the 74HC244 is about 5 volts, and adding this 300 ohm resistor will set this 7-segment display current to about 10 milliamps, which should be sufficient enough to light the LED segment which are here, all these 7 segments. Now let's see how we can connect multiple 7-segment display to the microcontroller. So in this slide we see there are 6 7-segment displays starting from 0. You can see this is one of them, and then you have 3 in between these 2, and then this is 4 and 5. So from 0 to 5 are your 6 7-segment displays. And port B, this is your port B, starting from RB0 to RB5 is your port B, and then starting from RD0 to RD6 is your port D. So you see how port B and port D together, they are driving the 6 7-segment display, and you can see this is the circuit. So these are the current limiting resistance connected to the these transistor, and then further it is connected to these 7-segment display, and then we have this buffer chip over here. So that's how you can connect using 2 different ports, and you can drive multiple 7-segment displays. And then decimal to 7-segment decoder. So you can see if you want to display digit 0, 1, 2, 3 and till 9, then this is the sequence you'll have to follow. These are the segments will be turned on, and then corresponding to this is your hexadecimal number. So for example, this represents 1110 represents your E, and then this represents your E, and this, which is from 0 1 1 1, represents your 7. And same with here. So we are assuming there is a 0 here, so 0 0 1 1 is your 3, and this is your 0, and then 1 1 0 is your 6, and then 1 1 0 1 is your D, and then so on. So the display or decimal digit on display I perform the following operation: configure both port B and port D for output, drive RBI. RBI is I is from 0 to 5. In this case, we were using, we saw in the previous slide, pin to high, drive other port B pins to low, output the hex value corresponding to the specific decimal digit to port D. Now next we have an example. Write an instruction sequence to display 5 on the 7-segment display 4. So what's it saying is to display 5 on which display? Display number 4. So this is the display number 4. We want to display 5 in this display, and this display is connected to RB4. Okay, so let's see what will be the solution. Clear F tris B, configure port B for output, and then clear F tris D, configure port D for output. Move literal number literal number to the working register 0 cross 5B. So this number is for a 5-segment pattern, and then move this this value from a working register to the file register port D, and then move literal value to the working register 0 cross 10, which means enable display 4 to light, and then move W to F to port B. So this one which you see here is this for RB4, which means 0001 and 0000. You're moving this to the port B so that this segment can be enabled. So you can see that how you can enable one segment at a time, and the same you can do for other segment as well, and you can put up different pattern over here based on the requirement. So this is the end of the lecture. Thank you so much for watching.